Amputation severely impede an individual's ability to perform simple tasks, leading to a poor quality of life. 65% of upper limb amputations are transradial, and current devices are too heavy, unappealing, and highly expensive. Our solution to these problems is ProAbility, a 3D printed transradial prosthetic arm. The use of 3D printing, in our case FDM, significantly lowers the cost, weight, and time spent to manufacture these devices, in addition to making them highly customizable. Our device uses myoelectric control, in which electric signals from the residual limb muscles are used to drive movements within the hand and fingers.
The production of an artificial limb requires speed, power, and a range of motion equivalent to its biological counterpart. Each finger was divided into 3 linkage segments that were powered by a gear motor, worm gears, and pulley-based mechanisms. After applying a plastic gripping mold to each digit, each finger was shown to produce 60 newtons of force within 1 second of muscle activation. The palm itself was designed as a motor housing unit that is capable of flexion, extension, and rotation due to rotary mechanisms within the wrist. The forearm then is hollow in order to accommodate for various electronic components, such as the customized PCB board and the Arduino Mega. From here, the actual socket is made of TPU and a pin lock mechanism that connects to an athletic fit sleeve socket liner. From the forearm, 2 opening flaps exist to a USB charging port and 2 adjustable weight cylindrical blocks. These, combined with the compressive straps, not only allow the user to control the arm freely, but control the forces that are applied to the residual limb.
To enhance the comfort of the device, our design features a cooling system located in the socket for temperature regulation. When the temperature sensor reaches either a default 30 degrees Celsius or a user-specified temperature range, the cooling systems are activated in a controlled response. Our design also features a vibratactile feedback warning system. With this system, when either the force sensors or the temperature sensors located in the hand reach levels outside the operating ranges, vibration modes are activated to warn the user. These vibration motors vibrate at different rates to distinguish pressure warnings from the temperature warnings.
EMG thresholds are an essential element of the software. They make the functionality of the prosthetic more precise. Placement analysis of the EMG sensors within the sleeve help determine the thresholds based on how strong the signal from the muscle was during the testing. The system is based on a proportional integral derivative control, which works by calculating the distance between an original point and a target position. As soon as the motor arrives to this target position, it stops all of the movement with the function interrupt from the Arduino Mega. The motor's encoder is a fundamental part because it provides feedback of specific positions of the motors.
Finite element analysis in console software digitally tests heat flow as well as structure integrity. When carrying out the overall tensile test on the prosthetic arm, the deformation was shown to be minimal, and the segregated solution generates the relationship between iteration number and error of heat transfer solid mechanics.
After analyzing our competitors and taking our fixed and variable costs into account, our device will sell for just $970. Looking to the future, an app would be a valuable implementation to socially connect prosthetic users, and game-based EMG training could be incorporated to enhance users' control ability.
Fused deposition modeling was used to produce most of our parts through ABS and PLA as an accommodating material. Through secondary manufacturing processes, we were able to produce a lightweight design that comprised of very cheap components. When the EMG sensors are receiving signals from their source, they power the Arduino Mega to produce motion in the DC motors, as well as the sensors that are on the fingertips are able to provide information back towards the arm in order to detect danger as well as conditions for movement. Issues that can arise with the arm include improper placement of the EMG signals, as seen here, showing very poor function of the arm. However, by adjusting the position with very specific recorded signals and thresholds, the arm can be produced with very specific movements.